We now move on to understanding the implementation of the Quoridor AI agent. We use Monte Carlo tree search algorithm for our AI agent. So the objective boils down to find the best strategy or the best move for a given state of game. So why Monte Carlo tree search algorithm? So the brute force game tree search algorithms are computationally very expensive as the game trees grow exponentially. For example, Quoridor has a branching factor of 60. So using MCTS, we can approximate the best strategy by randomly sampling the next moves and in turn exploring and exploiting the game space. First, let's look at the game tree structure of our game. So this is a typical node in the tree. Every node is basically a move in the game. We store its parent, its UCT, its number of wins, number of simulations. So these are the values that we use during the expansion phase, its children, and if it's a terminal node. Now, what is Monte Carlo tree search algorithm? So it can be divided into four parts: selection, expansion, simulation, and backpropagation. So selection, we start from a root node, the current state for which we are finding the best move, and select successive child nodes which have the maximum UCT till a leaf node is found. For example, we move to this node, and this node because they have the higher UCT values. Then we expand the game tree by adding the child of node L, the node C, to the game tree. So what is this UCT function? So the UCT of a node I is given by the number of times it led to a winning terminal state over the total number of time it was simulated plus this second term, which is inversely proportional to number of times it was simulated. So the first term represents the exploitation. If the node has a more higher winning rate, we tend to select it more during the future simulations. But we also want to explore the nodes uh, as we go along. So the inversely proportional relation to the NI, which is basically how many times it was simulated, gives us that. This gives us the that effect. So as the number of times the parent is simulated increases, so this fraction increases and UCT of that node increases and the probability that it will be simulated increases. So after choosing the C, we pass C to a rollout function that simulates the gameplay on that node C till a terminal state is reached. When a terminal state is reached, we update the UCT values of the previously simulated nodes in this whole path. So this updated UCT value is used for further simulations. This can be also explained in the code. So this is a selection part. If we find a terminal node, we directly pass it to a rollout. Otherwise, we select its child which have the maximum UCT. As we select the children of the successive children, if we find a leaf node, we pass it to a rollout function that simulates as in the phase 3. After this simulation process is done, we repeat this whole four phase process for given number of times and pick the child of the root node. So we were finding the best move for root node. Pick the child of the root node with maximum number of simulation. So the root that was simulated maximum number of times. And it can be seen here. Select best move. So we select the root child with maximum number of simulations. So what are the problems associated with Monte Carlo tree search? Again, MCT is slower as we increase the number of simulation for better approximation of the strategy, the computational complexity increases. So we introduce heuristics into the algorithm. that help to reach terminal state faster using the pre-known strategies that we know for Quoridor. So some of these heuristics are reducing the next move step set by considering the fact that walls are placed in the. So generally the slots are placed near pawns to obstruct the opponent or to help our pawn to move further. During expansion and simulation, we choose moves with shortest path strategy. So shortest path strategy is basically we follow the path that is shortest and leads to the winning the last row of the game with probability 0.07, and with other 0.3 probability we use the uh, regular strategy. So this helps to reach terminal state faster. Also, once the opponent is out of walls, the best strategy is just to follow the shortest path. We determine shortest path using breadth first search. So we implemented the whole interface using HTML and CSS, and we encoded the logic using JavaScript. So we would like to thank Professor Neeldhara and Professor Manisha for providing us opportunity to work on this project. This concludes the explaining the implementation of our agent. Thank you.